You pour a glass of cold water, you leave it on the table, the room isn't hot, there's no steam, no bubbles, no drama. So why does it slowly disappear? How can something cold evaporate? Isn't evaporation supposed to be about heat, about boiling, about energy, about things getting excited and flying off? Here's the strange part. The water doesn't need to be hot to escape. In fact, something far more subtle and far more beautiful is happening right under your nose. If you love clear thinking, real physics, and ideas that challenge your intuition without talking down to you, you're in the right place. Stay with me until the end, because once you see what's really happening at the surface of that glass, you'll never look at cold the same way again. And if curiosity like this excites you, subscribe. We explore physics the way it should be explored, with honesty, clarity, and a little bit of wonder. So before we can understand how cold water disappears, we have to slow down and ask a much more uncomfortable question. What do we really mean cold? Because when you say the water is cold, what are you actually describing? A sensation in your fingers? A comparison to something hotter? Or a precise physical condition? In everyday language, cold feels like the absence of heat. It feels like nothing is happening, calm, still, quiet. But physics is rarely impressed by how things feel. Imagine shrinking yourself down far smaller than a grain of dust, smaller than a bacterium, until you're hovering among the water molecules inside that glass. What would you see? You might expect stillness. After all, it's cold. But you wouldn't see stillness at all. You'd see chaos. Every molecule would be vibrating, twisting, colliding with its neighbors at enormous speeds, hundreds of meters per second. They're jiggling not because the water is hot, but because temperature in physics is not about comfort. It's about motion. That's the first shift in thinking. Temperature is a measure of how much microscopic motion there is on average. Not the total motion, not the loudest motion, the average. When something is hotter, its molecules move faster on average. When something is colder, they move slower on average. But slower does not mean stopped. Let me give you an analogy. Picture a playground full of children running around. On a hot day, they're energetic, running fast, shouting, colliding. On a cooler day, maybe they're calmer, walking instead of sprinting. But even on a cool day, no one is frozen in place. That's what cold water is like. The playground is calmer, yes, but the game hasn't stopped. In fact, even at room temperature, water molecules are in constant motion. They never sit still unless you approach absolute zero. And that's a whole different story. Now here's where it gets subtle. When we say temperature relates to motion, there's a very simple physical intuition behind it. For a moving particle, the energy of motion, the kinetic energy, depends on how fast it's going. In its simplest form, that idea looks like this. Genuine math block widget, always prefetched. Content, just notice something important. The speed is squared. That means if a molecule moves just a little faster, its energy increases a lot. So even in cold water, where the average motion is modest, some molecules are inevitably moving faster than others, and because energy grows with the square of speed, those few faster molecules carry disproportionately more energy. Now think about that glass of water again. It's not quiet at the microscopic level. It's a restless swarm. Molecules bump into each other, exchanging energy constantly. One slows down, another speeds up. It's like a perfectly fair casino where chips are being traded every instant. Cold does not mean no energy. Cold means less average energy. And once you accept that, once you really accept that cold water is still a storm of moving particles, you're ready for the next idea. Because if molecules are constantly jostling, constantly trading energy, then every so often, purely by chance, one at the surface might receive enough energy to do something remarkable. It might escape, and that is where the real story begins. And that is where the real story begins. Because now we're no longer talking about the average motion of all the molecules. We're talking about a very special group, the ones at the surface. Imagine you're a water molecule deep inside the glass. You're surrounded on all sides by neighbors. Every direction you turn, there's another molecule tugging on you, bumping into you, holding you in place through tiny electrical attractions. You can move, yes, but you're trapped in a crowd. Now imagine you drift upward until you reach the surface. Suddenly things change. Below you there are still neighbors pulling you back. But above you, empty space, air, freedom. At the surface the rules are different. A molecule there is only partially held down. It's like standing at the edge of a swimming pool instead of being buried at the bottom under a pile of people. So here's the key idea. Inside the liquid, a fast-moving molecule can't escape because it's boxed in from every direction. But at the surface, if a molecule happens to be moving upward and fast enough, nothing is there to stop it. Now you might ask, fast enough to do what? Fast enough to break free from the mutual attractions holding it in the liquid. Water molecules are not glued together like bricks, but they are attracted to each other. These attractions form a kind of energetic well. To escape the liquid, a molecule needs enough kinetic energy to climb out of that well. Think of it like this. Picture a ball sitting in a shallow valley. If you nudge it gently, it rolls around inside the valley but doesn't escape. If you throw it hard enough, it rolls up the hill and over the edge. The liquid surface is that hill. And here's the beautiful part, because molecular motion is random and constantly changing, every so often, purely by chance, one molecule at the surface gets just enough energy from collisions with its neighbors to roll over the hill. No boiling required, no bubbling drama, just statistics and chance. That molecule leaves the liquid and becomes part of the air, a vapor molecule. Now notice something subtle. This doesn't require the water to be hot. It only requires that some asterisk molecules at any given moment have enough energy. And since energy is continuously being shuffled around through collisions, that condition is always being met, even in cold water. It's a bit like a crowded room where people are passing coins around randomly. Most people have an average number of coins, but occasionally someone ends up with a small fortune just by luck of the exchange. If there's a door that only opens for people holding enough coins, eventually someone will walk out. That's evaporation. And there's another crucial detail. This only happens at the surface. Inside the liquid, even a fast molecule can't go anywhere because it's surrounded. But at the boundary where liquid meets air, escape becomes possible. So evaporation is not a bulk process like boiling, where bubbles form throughout the liquid. It's a surface phenomenon. A quiet, continuous leaking of the fastest molecules into the air. And because the process depends only on the existence of some sufficiently energetic molecules, not on the average being extremely high, it never truly stops. As long as the temperature is above absolute zero, there will always be molecular motion, always collisions, always a few energetic escape artists at the surface. Cold water doesn't need to be persuaded to evaporate. It's already trying. All it needs is a surface and time. All it needs is a surface and time. But now we have to confront a deeper question. We've been saying some molecules move faster than others. Fine, but how many? And how much faster? Is it just a rare fluke, or is there a precise pattern hiding underneath all this chaos? Here's where physics becomes both subtle and beautiful. Imagine lining up every single water molecule in that glass according to its speed. Slowest on the left, fastest on the right. What would the lineup look like? You might be tempted to think they're all moving at roughly the same speed, just a little bit different from each other. But nature doesn't work that way. When particles exchange energy, randomly colliding, bouncing, redistributing motion, the result isn't uniform. It follows a very specific statistical pattern. Most molecules cluster around an average speed. Some move slower than average. And a smaller but never zero fraction move much faster than average. It's like exam scores in a large class. Most students score near the middle. A few score very low. A few score very high. Even if the average score is modest, there are always some outliers at the top. Temperature sets the average energy, but it does not cap the maximum. That's the critical idea. Even in cold water, where the average kinetic energy is relatively low, the distribution always has a tail, a small population of molecules with significantly higher energy than the mean. And because energy grows with the square of speed, those high-speed molecules matter enormously. Let's make this more concrete. Suppose the average kinetic energy corresponds to some modest molecular speed. That doesn't mean every molecule is crawling along gently. It means most are. But statistical mechanics, the mathematics of large numbers and random exchanges, guarantees a spread. If you were to plot the number of molecules versus their energy, you'd get a curve that rises to a peak at the average and then trails off gradually toward higher energies. That trailing edge, that thin statistical tail, is where evaporation lives. Now think back to the surface of the water. A molecule needs to exceed a certain energy threshold to escape the liquid. Let's call it the escape energy. Most molecules don't have enough. They bounce around and stay put. But the molecules in that high energy tail, some of them do. And because there are unimaginably many molecules in even a small glass of water, on the order of 10 4, even a tiny fraction of high energy molecules corresponds to an enormous absolute number. So evaporation is not rare. It's statistically inevitable. Here's an analogy. Picture a stadium filled with millions of bouncing rubber balls. Most bounce to moderate heights. A few barely leave the ground, but a small number bounce unusually high. If the stadium has no roof, eventually the highest bounces will clear the walls. Not because the average bounce is extreme, but because the distribution guarantees outliers. Now here's a deeper insight. Raising the temperature doesn't suddenly turn on evaporation. It simply shifts the whole distribution slightly to the right. The average increases and the high energy tail becomes fatter. More molecules exceed the escape threshold, so evaporation speeds up dramatically. But even when the distribution is centered at a lower energy, even when the water feels cold to your touch, the tail never disappears. There are always some escape artists. This is one of the profound lessons of statistical physics. When you deal with enormous numbers of particles, randomness does not create disorder in the large-scale sense. It creates predictable patterns. Cold water evaporates not because it is secretly hot, not because it is boiling invisibly, but because probability itself guarantees that a few molecules will always have enough energy to break free. And once you see that, once you understand that evaporation is written into the statistics of motion, the phenomenon stops being mysterious. It becomes inevitable. And that inevitability is the quiet genius of nature. But now we have to clear up a very common confusion. If cold water is already losing molecules, if evaporation is always happening, then what exactly is boiling asterisk? Why does boiling look so dramatic while evaporation looks so quiet? Because these are not the same process. Let's start with what you see when water boils. You put a pot on the stove, heat it up, and suddenly bubbles form everywhere. Not just at the surface, but throughout the entire liquid. Those bubbles rise, burst, and release vapor into the air. That's boiling. Now compare that to the glass of cold water sitting on your table. No bubbles, no drama, just a slow disappearance from the top. So what's the difference? The difference is not simply more heat. It's something more precise. Boiling happens when the vapor pressure of the liquid equals the surrounding atmospheric pressure. That sounds technical, but the idea is simple. Inside a liquid, molecules are constantly trying to escape. When one escapes at the surface, it enters the air as vapor. But vapor molecules can also collide with the surface and re-enter the liquid. There's a kind of back-and-forth traffic. At lower temperatures, only a small number of molecules have enough energy to escape. The vapor pressure, the pressure exerted by those escaped molecules, is relatively low. But as you heat the liquid, the energy distribution shifts. More molecules occupy that high energy tail we talked about. More can escape. The vapor pressure increases. Boiling occurs when that vapor pressure becomes strong enough to push back against the surrounding air pressure. When that happens, vapor bubbles can form asterisk inside asterisk the liquid. Think of it this way. In evaporation, the escape is like people slipping quietly out of a crowded party through the front door. Only those near the door with enough motivation can leave. But in boiling, it's as if the excitement inside becomes so intense that pockets of vapor form everywhere like little balloons, and they're strong enough to push the crowd aside and expand upward. That's why boiling happens throughout the liquid. The pressure inside those vapor bubbles matches the pressure outside so they don't immediately collapse. At lower temperatures, if a tiny vapor bubble forms inside the liquid, it gets crushed instantly. The surrounding pressure is too high, and there isn't enough internal vapor pressure to sustain it. So evaporation is a surface process, boiling is a bulk process. Evaporation depends on individual high-energy molecules escaping from the boundary. Boiling depends on the collective vapor pressure of many molecules becoming strong enough to balance atmospheric pressure. Here's another way to picture it. Imagine you're underwater in a swimming pool. At shallow depth, you can blow a bubble and it rises easily. But if you dive deep, the surrounding water pressure is stronger. You'd have to blow much harder to create a bubble that doesn't collapse. In a liquid, the deeper you go, the more pressure from the surrounding liquid presses inward. To create a stable vapor bubble inside, the internal vapor pressure must match that surrounding pressure. Only at a certain temperature does that condition become possible, and that temperature depends on the external pressure. That's why water boils at a lower temperature on a mountain. The atmospheric pressure is lower, so the vapor pressure doesn't need to be as high to balance it. Evaporation, though, doesn't wait for that balance. It doesn't care about matching pressures throughout the bulk. It only needs a few energetic molecules at the surface. So when cold water disappears, it's not secretly boiling. It's not hiding bubbles too small to see. It's simply allowing its most energetic molecules to escape one by one from the surface, quietly, continuously, inevitably. So when cold water disappears, it's not secretly boiling. It's not hiding microscopic bubbles. It's simply letting its fastest molecules slip away from the surface. But now something even more interesting happens. If the fastest molecules are the ones escaping, what does that leave behind? Think about that carefully. We said temperature is related to the average kinetic energy of the molecules, not the slowest, not the fastest, the average. Now imagine you have a crowd of runners, and you suddenly remove only the fastest ones. What happens to the average speed of the group? It drops. That's exactly what evaporation does to water. The molecules that escape are not random in energy. They are selected from the high-energy tail of the distribution. They are the speed champions, the ones energetic enough to overcome the attractive forces holding them in the liquid. When they leave, they take that extra kinetic energy with them. And what remains is a population with slightly lower average energy. Lower average energy means lower temperature. That's why evaporation causes cooling. You've experienced this, even if you didn't think about it in molecular terms. Step out of a swimming pool on a windy day. The water on your skin evaporates. The fastest molecules escape into the air. Your skin loses energy. You feel cold. Or rub alcohol on your hand. It evaporates quickly and your skin temperature drops noticeably. The liquid didn't feel cold at first, but evaporation selectively removes energy. There's no magic here, it's just energy accounting. If you want to see the intuition mathematically, remember the temperature is proportional to average kinetic energy. When high energy molecules leave, the remaining average must decrease. No complicated equations required, just the logic of averages. Now here's something even deeper. Evaporation doesn't just cool the liquid, it continues until a balance is reached. As molecules escape into the air, some vapor molecules collide back into the liquid and stick. Eventually, in a closed container, an equilibrium forms. The rate of molecules leaving equals the rate returning. At that point, the vapor pressure stabilizes. But in an open room where air currents carry vapor away, that balance is constantly disrupted. Molecules keep escaping, and the water level keeps dropping. So when you see a glass of cold water slowly disappearing over hours or days, what you're witnessing is an ongoing statistical selection process. The fastest molecules leave, the average energy drops slightly, the system readjusts through collisions, a new high-energy tail forms, and the process repeats. It's like a lottery that never stops running. And here's the beautiful part. This cooling effect is not an accident. It's a fundamental consequence of how energy distributes itself among enormous numbers of particles. Nature doesn't need a thermostat or a supervisor. It just follows probability and conservation of energy. Cold water disappears because motion never stops. Because probability guarantees outliers. Because surface molecules can escape, and because when they do, they carry energy with them. What looked like a quiet glass sitting harmlessly on a table turns out to be a dynamic statistical machine, constantly exchanging energy, constantly adjusting, constantly evolving, nothing dramatic, no boiling bubbles, no visible commotion, just molecules, motion, and the quiet logic of physics doing exactly what it must. So let's step back and look at what we've uncovered. A quiet glass of cold water sits on the table. No bubbles, no steam, nothing dramatic. And yet, molecule by molecule, it vanishes. Not because it's secretly hot, not because it's boiling invisibly, but because temperature is motion, and motion never truly stops. Inside that glass, molecules are constantly colliding, exchanging energy, reshuffling speeds. Most move at average energies, some move slower, and a small but inevitable fraction move faster, fast enough to escape the liquid surface. Evaporation isn't a switch that turns on at high temperature. It's a statistical certainty built into the distribution of molecular energies. Boiling is a bulk phenomenon, bubbles forming when vapor pressure matches atmospheric pressure. Evaporation is quieter, it's a surface phenomenon. The fastest molecules leave first, and when they do, they carry energy with them, lowering the average energy of what remains. That's why evaporation cools. So the strange reason cold water disappears is not strange at all once you look at it the right way. It's probability. It's energy conservation. It's the restless motion of atoms doing what atoms always do. And I think that's the real beauty here. The ordinary becomes extraordinary the moment you ask the right question. If this way of looking at physics, peeling back the surface of everyday things and finding deep principles underneath excites you, then you're exactly who this channel is for. Subscribe, and let's keep exploring. There are mysteries hiding in the simplest objects around you, in light, in heat, in motion, in time itself. All it takes is curiosity and the willingness to look a little closer. Thanks so much for sticking with me through this little journey into the world of molecules and motion. I love exploring these everyday mysteries, and it's even better knowing someone else is curious about them too. Keep asking questions, keep noticing the little things, and never stop wondering how the world really works. I'll see you in the next video.